Imagine standing at the edge of an ocean so deep, so utterly unreachable, that Mount Everest could sink into it and vanish without a trace. Now imagine that ocean isn't water. It's molten metal, hotter than the surface of the sun, crushed under pressures that would turn diamonds to dust. And at the center of that inferno, suspended in the dark heart of our planet, spins a sphere of solid iron larger than the moon. We call it the inner core. And recently, scientists discovered something impossible. It stopped. Picture a ball of iron the size of Pluto, floating in an ocean of liquid metal, 5,000 kilometers beneath your feet. The temperature? Over 5,000 degrees Celsius. The pressure? 3 million times what you're feeling right now, sitting wherever you are. This is the engine room of planet Earth, the furnace that powers the magnetic shield protecting you from solar radiation, the force that keeps continents drifting, volcanoes erupting, earthquakes rumbling. For decades, we knew it was spinning, faster than the rest of the planet, a cosmic flywheel keeping everything running. Then, in early 2023, researchers published something that sent shockwaves through the scientific community. Not just a headline, but a revelation that rewrites what we thought we understood. The core had decelerated. Some data suggested it stopped entirely. Other measurements hinted at something even stranger. It might be rotating backwards. The question everyone started asking wasn't just, how is this possible? It was, should we be worried? To answer that, we need to go back. Way back. To a time when we didn't even know the core existed. Think of Earth like a cosmic egg. The shell, the crust, is thinner than the skin of an apple when you scale it down. It's the only part we've ever touched. The part we build our cities on, dig our minds into, fight our wars over. Crack through that shell, and you hit the mantle. Don't let the name fool you. This isn't empty space. It's rock. Solid rock. But over geological time, it flows like honey, dragging continents across the surface in a dance that takes millions of years. Keep descending. Past the mantle's slow churn, you punch through into the outer core, a roiling sea of liquid iron and nickel, churning in convection currents that generate Earth's magnetic field. This is the dynamo, the reason compasses point north, the reason life survived long enough to evolve. And then, at the very center, you reach it, the inner core, a solid sphere of crystallized iron, spinning in the darkness like a planet within a planet. But here's the catch. No human has ever seen it. No probe has ever reached it. No drill has ever come close. So how do we know any of this is real? The deepest hole humanity ever dug is in Russia, the Kola Super Deep Borehole. 12 kilometers down. It took 20 years to drill. The core is 500 times deeper. We'd need a different approach. Something indirect, something clever. The first clue came in 1896 from a scientist named Emil Weichert. He did something simple. He weighed the Earth. Not literally, but mathematically, using gravity, density, mass. And when he crunched the numbers, something didn't add up. Earth was too heavy. Way too heavy to be just rock. There had to be something dense at the center. Something metal. He guessed iron because meteorites, the leftover building blocks of planets, are packed with it. He was right, but he had no proof. The proof came 1 year later, in 1897, from Richard Oldham. He was studying earthquakes, and he noticed something strange. When an earthquake strikes, it sends out waves, vibrations rippling through the planet like sound through a bell. Two types of waves, specifically. P waves, pressure waves. They compress and expand the material they pass through, like a slinky. They can travel through anything, solid, liquid, gas, S waves, shear waves. They move side to side, like shaking a rope. And here's the key. S waves cannot travel through liquid. They need solid material to propagate. Oldham watched the seismographs. He saw P waves appearing on the other side of the planet after an earthquake. But S waves, they vanished halfway through. Conclusion: there's liquid in the center of the Earth. But the story didn't end there. In 1929, a Danish seismologist named Inge Lehmann was analyzing data from a massive earthquake. She noticed P waves showing up in a place they shouldn't. A shadow zone where the geometry of Earth's liquid core should have blocked them. Unless there was something else. Something solid, deep inside the liquid core, deflecting those waves back up. She'd found it. The inner core. A hidden world proven to exist without ever being seen. Fast forward to the 1960s. The Cold War was in full swing. The United States and Soviet Union were detonating nuclear weapons underground, testing bombs in the desert and beneath. Remote islands. But they needed to monitor each other, to make sure no one was cheating on test treaties. So they built a global network of ultra-sensitive seismographs. The goal? Detect secret nuclear tests. The side effect? A revolution in Earth science. These new instruments could pick up vibrations so subtle, so precise, that scientists started noticing something extraordinary. Seismic waves didn't travel through the inner core at the same speed in every direction. If you sent a wave north to south, it moved faster. East to west? Slower. This wasn't random. This was structure. The inner core had a grain, like wood, like a crystal. As iron crystallizes under unimaginable pressure, the atoms align. And when a planet has a magnetic field threading through it, those crystals orient themselves along the field lines, north to south. This anisotropy, this directional grain, became the key to the next great mystery. Because if the grain changed over time, it meant one thing. The core was rotating. Here's where it gets wild. In the 1990s, scientists developed a new technique. They called it earthquake doublets. The idea: find two earthquakes that happen in the exact same spot, decades apart. Same fault line, same depth, same energy release. Identical twins, separated by time. When you compare the seismic waves from both quakes, you'd expect them to look the same, right? They didn't. The waves that passed through the core in, say, 1964 traveled at a different speed than the waves from an identical earthquake in 1995. The grain had shifted. The core had rotated. At first, scientists thought it was simple. The core spins slightly faster than the rest of the planet, a phenomenon called superrotation. Maybe a fraction of a degree per year, but measurable. Then, in 2023, two separate teams, one at Peking University, one at USC, published findings that flipped the script. The core wasn't just spinning faster, it was oscillating, speeding up, slowing down, even reversing direction. All part of a cycle roughly 70 years long. The core hadn't stopped. It had reached a turning point, the moment where it pauses before swinging back the other way, like a pendulum, like a heartbeat. So what does this mean for us? For life on the surface? Turns out the effects are real, but subtle. When the core changes speed, the length of a day shifts, not by hours, not even by seconds, by milliseconds. Imperceptible to you and me, but measurable by atomic clocks. The magnetic field flickers too. Small variations in strength, tiny wobbles in the poles. Nothing catastrophic. Nothing that threatens the shield protecting us from space. This isn't a disaster. It's a rhythm. A 70-year pulse beating at the heart of our planet. A reminder that Earth isn't static. It's a living, breathing machine, constantly adjusting, recalibrating, balancing forces we're only beginning to understand. We've never seen the core. We never will. But we've learned to listen to it. And in doing so, we've discovered something profound. Beneath our feet, in the crushing dark, spins a mystery as old as the earth itself. A mystery we're only just starting to decode. The inner core keeps its secrets close. But we're getting closer.